module hacks into the internals of the core operating system, changing its behavior. In this series, we're going to code a kernel module which will hijack the kill system call, disable it, and replace it with our own function, and thus creating an immortal process. Let's get started. Sup guys, welcome to today's show. Today we're gonna do exciting stuff. We are gonna try to code our own Linux kernel module. So the Linux kernel is the core operating system, and adding a module to that can let us affect the system deeply. So this is the general idea for today, the goal anyway. I have not tried out this example, so we'll learn together. So basically, if you have a process, let's say, let me just create something temporary, a simple bash script that does while do. So this will just do nothing, basically, an endless loop that sleeps 1 second. What did I call it? tmp.sh. We'll run this, and if I check the running processes, I'll try to find this script. Let's grep for tmp. There it is. So in Linux, you can stop and exit processes by killing them. So you type the command kill and then the process ID number, the PID. And as you can see, it terminated. You can make your processes a little bit more resilient if you block those kills. So let's see how we do that. I think it should be possible. I don't remember how to do it in bash, but you can easily do it in C, for example, using the signal syscall. But if you have coded something that blocks those kills, you can always kill it using -9. That means that you will kill the process very violently. It will have no real chance to recover anything. And as you can see, it was killed. So there are different levels and different signals you can send to the processes. What I want to code is I want to code something like the immortal process. So you select the one process which will be the immortal process, and then even if you kill it, it will not be killed. What is dead may never die. So how to do that? Well, we need to replace the system call. If we look inside of Linux and how its internals are working, there is a system call kill, which sends one of these kill instructions to a process. Um, so basically we need to hook into this signal system call inside of the kernel, replace it with our own function. So every time someone tries to kill something, our function is executed instead. And if it is our immortal process, then it will just give an error message or something. And otherwise, it will run the original process. So that is the general idea. And I have coded a lot of different kernel modules during the years, um, both hardware device drivers and computer security tools. Um, but that was a while ago. The last time I wrote something like that was for kernel 2.6. And my current kernel is 6.1. So a lot of things have changed. And because of that, I am going to cheat a little bit, only a little bit, and I'm going to take help of two web pages that I found. And I will leave the references in the video description. First of all, the Linux kernel module programming guide, which will help us write our first module, which will simply be a hello world example, basically. And this is a programming guide which is open source. And then for the more advanced examples, when we will try to hook into the syscall table, I found this Bruno Ciccarini website, or rather GitHub page. I don't know what it's called. Anyhow, this is a GPL, open source 3.0 license. So that is also available to us. And this is a simple guide how to hook into the system calls and change them. And I'm not sure if this technique is going to work on my kernel, but let's try it out. And otherwise I have to change kernel or change technique. But that's the plan for today. Quite exciting stuff, huh? So let's begin by trying to code this hello world style example. And we need to first download the Linux kernel headers. Otherwise we can't really compile this thing. So let's see if we can find this. I will do apt cache search, and I will search for kernel, and I will grep for headers. Okay, we got a lot of stuff. And I am running 610 18. Maybe we should grep for this version. But maybe this last number doesn't matter. I'm not sure actually. Can we search for that specifically? What if we were to take this and we do apt cache search and we give this and 18? No. It's a little bit weird that they don't supply that. Will it work with 18? Probably the code will work, but I'm not sure if it will accept it. I think it has some kind of check for the right version. What if we were to upgrade the kernel? If we search, let's take this 26 one. If we just search for this version, let's see, Linux image, Linux for older PCs. That's a little bit funny. Linux for modern PCs. RT. What's my current? Let's see what the package name is for this one. If we do -list 610 Linux image blah 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 PAE. Okay. So if we were to take this one, let's see. It does not say what version it'll choose. Maybe that doesn't matter. It will probably choose the latest version. Ah, here we are. This is the one that we want, I think. So we'll do apt-get install, and we'll install the latest kernel. And before if you wanted another kernel, you would have to download the sources, compile the kernel, and come back the next day, basically. But nowadays there are pre-compiled images for that version of the operating system. And I even think that it will update the master boot record with the new image automatically. It was a while ago that I did any updates of the kernel. We'll see what happens. Meanwhile, we can start by creating a make file. So we can compile this stuff when it's due time. Let's see how we can make. Here is an example that we can get influenced by, is it? So I have created this kernel directory, which is linked to my Linux server. And let's create a makefile. And we need this obj_m thing. And we'll set it to our module. Let's call it hello.ko. And we need to save the current working directory. And then we need an all, and we can run make like this. And then we need the directory of the modules. So let's say that is moddir for now. And let's include build as well in that. And what did they pass? M is equal to our current directory. Modules. And clean does basically the same thing. Only we add clean to the end, I suppose, instead of modules. Okay, let's save this. And let's also check that directory. So how did they do it? They do unim-r. Let's see. Systems then will not be added to grub configuration. Check grub disable OS probe, blah, blah, blah. Not sure if it actually updated the grub stuff. Well, we'll see, won't we? Let's try rebooting this thing. Currently, we have the kernel 6.10.18, and we will have the same thing but 26 at the end, hopefully, when we reboot. All right, let's try shutdown -r now. Still responding. Come on. It's a little bit weird. Well, I guess I have to go to the console. So let's see, cloud. And my virtual machines are hosted on my own cloud platform using this VMware stuff. So let's see, Intel 32. Let's open up remote console. Okay, it rebooted. And it came back. That's pretty good. So let's see. Yes, we can connect to it. What is the kernel? 26. All right, good. Now we can begin really doing this stuff. So we need the kernel headers. Let's search for them again. So we do apt cache search, kernel headers, and we want 6.10.0.26. Okay, and we have this PAE version, right? Yeah. We did, didn't we? I can't remember. Let's see. Linux 6. No, this is wrong. I meant to list. PA. All right. So we'll do an install for this stuff. Yes. Nope. Maybe we need to update. Okay, this looks a little bit better. Okay, so now it's installed. Let's recreate my screen, by the way. And if you don't know, Screen is a program which lets me have multiple windows open at the same time. No, they only show one window, but I have several which I can switch between. So while do sleep one done, and this is just so I don't close the last one accidentally and exit the program. And I created a TMP and a kernel, and this will be my new home. And it uploaded our makefile. Let's delete this TMP thing. Right. So we need to find the directory where the kernel header files are stored, or the kernel modules, maybe both. So let's do uname-r, this thing, and lib module, what it is called, lib modules, and this version, and build. Yeah, seems legit. So let's take this directory and put it inside of our makefile. What did you call it? Mod dir, like so. And we have ourselves a makefile. All right, so let's try creating some hello world example of this thing. I don't want to do this because they are using the old method. Let's see if this is the right one. So basically, all modules require at least one thing. some initialization function which is run whenever the module is loaded, and it should return 0, otherwise it failed and will not load. And we need an exit function as well, which will run when the module is unloaded. And then we use these macros, module init and module exit, to specify which function is which. And you can also specify a license, and I think you should actually, because if you don't, I think you get some kind of error message or warning or something when you install the module. And there's not a lot of header files that are mandatory. Actually, we don't even need this, but well, in our example we will need it, but these two will be needed for all modules, and this is needed if we want to print stuff to the kernel log. So we get things like print k, and which basically works like printf, and these macros like prinfo, which print something to the kernel log with the log level info. So let's see. Let's create a sample module with init module and print k. So let's call this hello.c. And LKM means Linux kernel module, and that is usually the abbreviation which is used. And we need to include, and we can't include, by the way, stuff like stdio.h, because all these things live inside of the libc library. And we can't use that when we call it kernel modules. We need to go lower, so to speak. So we need to include module.h. We want to include, what was the other one? init.h. And we also want print k.h. And we will define our functions as static, so it only lives inside of this .c file. And this underscore init thing is like an attribute. It basically tells that this function can be unloaded after the module has been successfully loaded. So it's a memory optimization thing. You don't necessarily need this, I think. But let's do this properly. And we can call this function whatever we want. Let's call it setup. Does not take any arguments. It can, by the way, you can give arguments to the insmod command, which installs the module, but you don't use it. You don't put it inside of the function like this. All right, so let's use the prinfo, or yeah, let's do that. And let's say something like our LKM successfully loaded, like so, and we return 0, which is the okay thing. Let's also create an unload function, and that should be a void. And same here, basically, we say that this doesn't need to take up any additional memory. Let's call this unload, and no arguments, and we can simply do something like lkm unloaded. And then we run those macros. So module init should be our setup, and module exit should be unload. Module license can be GNU public license. All right, so that is basically the same thing that they did. Let's see if our, okay, it's not synced up. Of course I got disconnected when it rebooted. No, it wasn't really disconnected. It was in some kind of half state. Now it works. So let's save again. And there we have it. All right. So let's see what happens if we run make. Let's see. Did I forget to paste in the... no, it didn't update the make file because I was disconnected. Now I think it should work. Something is happening. Okay, we got a bunch of files. But I guess the interesting one is this hello KO. If we do lsmod, we see all the different modules which are loaded. So let's do lsmod and grep for hello. We get nothing, and we need to install it by using sudo insmod hello ko. We didn't get an error message. That is good. And it is here. Look at that. And let's check the kernel logs. Okay. Out of 3 module taints kernel. Module verification failed. Signature and a required key missing. Okay, I think these are only warnings, right? Let's see, maybe we need to do journal, kernel tail. Okay, maybe I need to do sudo as well. It doesn't seem to work actually. Required key. That must be some kind of new security feature, I suppose. Let's Google. Linux kernel module verification. Let's see. Manual assigning modules. Let's see if we have this file. Let's download the Linux kernel sources. Apt-cache search 61026. It used to have sources, Linux grep source. Let's see what we get. It does only say Linux source 6.1. But hopefully it contains the stuff we need. Well, we have this Linux config that might contain some of our stuff. Well, let's see. We are learning together. That's something, isn't it? User source And we need to have my ls alias, or this become excruciating. And let's unpack this thing. XC. I'm used to GC. How do we unpack XC? Is there something like xzip-d? Nope. What if we do tar-help grep xc? Okay, we can pass big J. So let's do tar jxf and this one. So the big J is for this xzip thing. The X is for extract, and F is the file that we want to use as input. So now we are basically unpacking the xzip and then at the same time untarring the stuff. Okay, it went pretty fast. So let's create a symlink for this source thing. And then if we go to scripts, do we have this? What sign file? Well, we have the source for it. Can we just do make sign file? We can certainly not. Open SSL. Everything seems to be related to OpenSSL. Don't I have OpenSSL installed? Maybe we need some. Or, by the way, maybe it does only need to, we need to add some switch to it. So let's try doing this instead. And we give L crypto, I think it's called. Huh, it worked. All right, so now we just need to find the keys that we need. Sign key.priv, do we have that? No, it wouldn't be included inside of the sources, right? Perhaps in this config thing. Let's install this xzip thing. It seems to be the latest thing. And let's do for everything in here, we do xzip-d. I am done. Didn't I just install xzip? Mm-hmm. user games exif. X interface to the C code interpreted, and that's probably not the right thing. Okay. Maybe we'd use the regular gzip. Weird thing. No. Is there something called X unzip? No. What is this thing? Seems to be a regular zip file, but I'm not sure I trust that. But let's try. Linux, how to extract XC. No, not GC, XC. XC utils. So apt cache search XC utils. There we have it. So now we have XC. Do we have unXC? No, we do. That's pretty nifty. So for X in everything, do unXC X done. That's more like it. But this is only the configuration files. So where can we find this signing key? What if we search the disk for this file name? It must be saved somewhere, right? So let's see. If we do find slash and we look for this dash print, and we don't want any noise. So let's see what we get. Nothing. Debian kernel module signing key. All these new Linux features are driving me crazy. I think it should be somewhere in the boot. Config init.rd. I think this whole thing is weird, actually. So how are everyone coding their drivers if it's not possible to get this key? But This can't be the right thing because I don't even have Wi-Fi. At least not on my virtual machine as far as I know. If you reuse a Debian kernel config file, you may need to disable module signing or enable signing with an ephemeral key. The Debian distro CA key is built into the shim binary itself, but there is also an extra database of keys that can be managed by the user. The user keys are called machine owner keys. Keys can be added and removed, blah 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 blah, mock util. Var lib. Let's search for this DKMS thing. We don't even have it. What about mock? Weird stuff. Well, let's try this guy then. Let's install this mock util thing. There is no mock util. Let's create an OpenSSL certificate. Okay, so now we have the key and the certificates. Now we need to import this thing. Okay, we can't really do that. Let's try signing with this anyway. So let's go into the kernel sources directory and let's go to scripts and we run this sign thing. Our algorithm is SHA-256 root book. Is it the previous? And then we give the certificate. And we give the name of the module, which is where I think home, JOBJ, and where is it? It's in TMP and then in kernel, and it's called hello.ko. Okay, so now it's signed at least. Let's remove the old one. And let's try to install this module. And let's check the kernel logs. Huh, it works. Our LKM successfully loaded. What do you say about that, guys? All right, let's take a short break. All right, you guys, welcome back. So before the break, we were finally able to load our LKM, our Linux kernel module, and we can also successfully unload it. And currently it is unloaded, I believe. No, it's there. So let's try to remove it. It's no longer in the list. Yeah, it seems to be a little laggy, the messages, but it'll show up. All right, so what is the logical next step? Well, we need to be able to find something called the syscall table, or SCT. And that is what it sounds like. It's a table of the operating system calls. So basically it looks something like this. And this is defined inside of the Linux kernel. So let's say we have an array of void pointers, which is called syscall table. And then we have some index. So for example, number 1 in this array is the address to exit. So this is the exit function or exit system call. And number 4, for example, is sys write, which is the write system call, which you can use to write things to a file or to the screen. And there are some 200, 300 different system calls, and they all have their unique number. So basically this sysexit is what is put right here. And then somewhere there are these definitions. So sysexit is 1 and syswrite is 4 and so on. So this variable, this table, syscall table, is inside of the Linux kernel somewhere. And back in the days, back in the kernel like 2.4 and 2.6, it was very easy to find this because it was exported like a regular symbol, like a regular exported variable. So you could just include some .h file, and then you can get the address of the system call table. And well, when we have the address, if we want to change, for example, let's say we want to change the write system call, then we can just point this variable, this part of the array, to the address of my own function. It's probably this, by the way. And then I can define this function, so it'll be something like int my own write, and it takes an FD, it takes a buff, and it takes some int size. And then I can control it entirely. And if I save the old address before I do this, so I'll do something like, let's just do void pointer to make it simple right now. Let's say I have this pointer and I set it to equal syscall table syswrite, and then I do this change. Then I can do whatever I want right here. Maybe I check for a specific string inside of this buff and then handle it differently. And I can, for instance, return -e perm, and it will be permission denied for executing that write system call, even if you root. And I can also just do return pointer and send all the parameters, and it will return the original write functions return value and side effects. So that is the general idea, how we want to do this, but we need to be able to find this syscall table because there are a couple of new hurdles trying to stop us from doing that. Plus, there is a write protection inside of the CPU, which we also need to circumvent. So that's why I'm following this guide, so I can see if I can find the syscall table and alter it. And when we can do that, we can code on our own exactly what we want. And I mean that in the literal sense. We can code exactly what we want to do because we're inside of the kernel and have all the privileges that are available. So let's see. Let's move on and see if we can find that syscall table. I read some stuff. Let's see. I think it was on this page. System calls. There is this file. And if we're lucky, we can find the address to the system call table inside of this file. But something is telling me that we are not that lucky. However, we do need to try that first. So grep syscall table from this file. Nothing. What if we run it as root? Nothing. Okay, then we have another possibility. There is this system map thing on some Linux distributions, which has a saved version of this. Sometimes it's a little bit scrambled, but let's first see if it's there at all. So boot system map something. And I need to do my aliases. Let's do this. All right, so what do we have? System map. We do have this. And the 26 is our current kernel, right? Yes. All right, so let's see. It's this one. If we grep syscall table from this file, we get nothing. Syscall table. And if we grep it from the older kernel, are we luckier then? No. It's a very small file, by the way. The real system map is in the Linux image version debug package. That's pretty interesting. All right, let's see if we can't install that then. So let's do an apt cache search kernel. We grep for our version. And then we grep for debug. No, not like that, like this. There's something. Let's install this thing. it's a big one. Almost 1 gig. Meanwhile, let's take a little look at how they do these things. So now I'm at this other page. Bruno Cicerini, I don't know, GitHub page or whatever it's called. And I have a link in the description. So let's see, hello world and some other stuff. Here is another variant. If we're not able to find it manually, we can try this thing, which basically, if you're familiar with GDB or debugging in general, you can set like a breakpoint somewhere in the code, and when the execution of your program reaches that point, it pauses. This is similar, only you do it on the CPU hardware level, basically. So you replace the first byte of an instruction with a specific thing. I think it might be an int3 or something. I don't know exactly. But when it reaches that breakpoint, you are able to take a look at the registers. And that's what this does, basically. It uses this technique in order to find the syscall table. And this does not work on all kernels either, but it's another thing that we can try if what we're doing right now fails. Then we need to get past the CPU level protection, the write protection, because the system call table is read-only and it's protected. So basically there is a CPU register, which is called CR0, and it contains different flags. So let's say it has this content. This flag means something on and off. This means something that can be on and off, and so on and so forth. 0 means on, 0 means off, and 1 means on. And if we look at this thing, 10,000, I think that means 65,536. Probably. Never mind. So one of these bits we need to change from a 1 to a 0, and then we are able to alter the syscall table. And then we can change this back afterwards. And it's pretty easy. Since we are in kernel mode, we have all the privileges. So we can simply just move, if we send the assembly instructions, and let's say we move into AX the contents of CR0, and then we can alter the EX register, and then we just move it back into CR0 like this. So that part is not very problematic, I hope. But yeah, finding the syscall table is the toughest thing, I think, unless what we're doing right now is successful. But let's work a little bit on our infrastructure. Let's create a new file and let's call this. So this will be step 2 out of 3 basically, with step 1 being the hello world, and this is going to be just a test to see if we are able to influence the syscall table. So let's call this syscall table.c. And the last step is creating our immortal process, which should be rather simple actually if we manage to get the other stuff to work. So let's see, we need to include Linux module.h, Linux init.h, and Linux printk.h. And we need some initialization function, and what was the return value? Int, I think. So let's do int, we need to make it static. Static int, and it's an init function. Let's call this setup again. No parameters, like so. Let's also be good and include the signatures. We're also going to have a static void exit cleanup void. So static void exit cleanup void. This just returns, and this for now will return 0. And at the end we need those macros. Let's see if I remember. I think it's module init and then the name of our function. And same here, module exit and our clean up with an N, not an M. And finally, this license thing, module license GPL. Let's see if I remember correctly, because I have only written this once before, and that was like 15 minutes ago when we did it together. And let's see if I remembered everything. So let's see, static int init and this, static void exit and this, module init, module exit, module license. Yes. So that's the power of my so-called copy paste rule. And it's no copy paste. No copy paste. And basically my copy paste rule says never copy paste, nothing at all, and not even your own code. Rewrite it each time and you will remember everything about the language after a while. Okay, so now this is installed. Does it install inside of boot, perhaps? No, that would be a little bit weird, right? So where will it go? The rest is inside user source Linux, I think. But here we have, no, that's not it. Headers, kbuild, no. All right, there is some flag to the Debian package manager to list its files, but I can never remember it. It's nothing you do every day. But dpkg, and let's try L. There we go. And no, not that. Let's grep for system map. User lib debug boot. Of course, where else? Okay, this is a little bit bigger, isn't it? 87,000 lines. So if there are 87,000, one of them should be the syscall table, don't you think? Let's hope. Okay. There we have it, I think. It's a very weird address, but perhaps the addresses are weird inside of the Linux kernel. But it can also be scrambled. Sometimes these are offset by something. I read about it in this one. Let's see. Yes, there's something called Kassler, which is randomizing the address every time, and every time you reboot, and it also offsets it a bit. So look here, for example. If we look at the syscall table from this proc call sims, the first thing we tried, here we have, and why are the addresses so long with a lot of F's in them? That's because this is a 64-bit system and I'm on a 32. So my addresses are like these. And as you can see, they're pretty similar, but not entirely. This ends in 13A0 and this in 23E0. Right. But these are both from the call sims, I think. This is the example. Here are the two different addresses for the same thing, but one is from system map and one is from call sims. But I wonder which is the correct one. If the address of a symbol in callsims is different than in system map, Kassler is an. Okay, so we should be able to check it for some other thing other than syscall table specifically. What about the print K? I'm not sure if it's exported, but it should be, right? Grep print K from this. Alright, we got a lot of different things. Let's do a better search. So extended search, and we want the line to end after this. And we do also want the word to begin, maybe like this. Or maybe this. Okay. Helpful message, at least. Even though it does not work. Let's just do space. Okay, there is no, just print K. But let's do console print K. So let's save this, and a trick I often do is I put a hashtag and I paste and I press enter. Then I can find it in my backlog. And let's see if we can't find this thing inside of proc call sims. We cannot. Do we find anything in this God-forsaken file? We do. So let's go from here instead. I don't know, let's just take something, flip SMM bit. And let's see if we can find this thing. Inside of where actually? This. Okay, there's something. So let's compare these two addresses. The one from call sims is bigger. What if we were to do if we echo this, and let's do 0x in front and minus this. This is the difference, and this in hex is seems pretty chosen, doesn't it? And now we select another thing from this file. Let's save this. And let's see which one it's which db the lower one was from, let's specify that because I will forget it again, lower from system sysmap. And then let's find something in call sims again. Let's take something a long way from it. Kick process. That's a good enough choice, right? So let's copy this. And which one was which again? Lower is from sysmap. So what we did was we did call sims minus sysmap, right? Let's find our offset again, this one. And then we take this lower from sysmap. If we take this one and we do the same, we echo, or we do the reverse, actually. No, do the same. So we take this from call sims and we minus this. We need a dollar sign as well. And then we take the hex of this. And if I have calculated this properly, we should be able to find this inside of sysmap. And if we search for this address, we should find that kick process. Let me just find the name of that file again. No, I can't. Let's do something like sysmap is equal to this. And we grep this from sysmap. We do not get anything. Bummer. If we grep kick process from sysmap, we do get something. And it's in the same ball. It is the same. Aha! I should not include the 0x at the end. Look, it is the right one. So all we need to do is we take the one that we find inside of sysmap and we do it the other way around. So we add this offset. So if we grep syscall table from sysmap, and we take this 0x this, and this time we plus this offset. And we hex this thing. And this should probably be the address of the syscall table, I think. Exciting stuff, huh? So, can we verify that somehow? That it is the correct one? I suppose we could grep it from call sims, but that shouldn't give us anything, I think. No, since it's not exported. We could possibly try something. Well, let's assume this is the right one, and let's create this trial and error test case. So let's define syscall table, or no, let's not call it that. Let's just call it SCT. And that should be 0x this, no, just this. So that is the address of the syscall table. We also need a variable, and I guess we should make it a void star, a static void star syscall table. Or maybe a pointer to a pointer. And when we load, we set syscall table equal to SCT. And let's obtain something from it. I'm just trying to figure out some example which will not crash my machine. Well, let's try to replace the kill instruction. Since we're going to use that anyway, let's just do that. And let's go to user include, and let's search for, I think it's number kill. And this is the right one, unistd32.h. $37. Okay. So what we want to do first of all we need signature, so let's do man to kill. Funny enough. We take this signature. Let's see if we paste this in, and we can do this, 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 and we want to turn this into a function pointer. Let's call this original kill. So I think this is the syntax. I don't do this often enough. So then we can set our original, and let's also make this static. Then we can set original kill equal to SCT 37. Right. So far, so good. And maybe we could just try to execute that function. So if we were to run original kill against some PID and some, let's choose some process that will live on. Let's see. 1 second. Which one is my current one? PTS 0. Let's try if we can kill this one. 828. So basically what I'm trying to do here is when we load this module, I will try to kill this specific process by running this function. And we also need to have a level. Let's see, man to kill. Let's open this signal.h and search for kill. Can't do like that. Let's go into include and let's search this and current and other directories for sig kill. Yeah, it's just 9. Okay. Oh no, I closed the wrong window. But we do still have this 828. Yes, this is my. So basically this is my login shell, so I should be disconnected when we launch, when we insert this module. TMP kernel. Set this to our home, and let's see. Yeah. So this should be 9. And then we try to return -e perm. No, we cannot do that. Let's return 0. Yeah. All right. I think this should work. Let's update our make file, and let's change hello.o to sct.o. And I lost the command where I signed this thing. Let's see if I remember how I found that page. I think it was one of these. Yeah. Here it is. Okay, we have created this, what it's called, it's the certificate. Let's, by the way, move these files. So both mock files should be put inside of home, jobj, and tmp kernel. And let's go here and change ownership. Like so. And then we copy this command. And we need to alter this slightly. User lib Linux, no, user source Linux. Script sign file SHA-256, and this should not be root. Let's just do this. And then we have the name of the file. So let's see, make this CM modules. maybe we can do something like this. Object should be SCT. And from that, we derive object.o. And let's change this to build. Let's create another one for sign. Where we do this for our object KO. And we run first the build and then the sign. And let's set clean as phony. Okay, let's see if this works. No. Conflicting type for syscall table. Previous declaration of syscall table. That's weird. But okay. I suppose this works as well. So const syscall. Never mind, I think this is okay. But let's call ours this instead and see what happens. We should probably do syscall table 37. Okay, let's try again. Got a little bit closer. Wording assignment avoids star from unsigned int, makes pointer from integer. Syscall table equals SCT. Let's do an intermediate thing then. Let's define a null pointer. Which is 0. And we set syscall table equal to our null pointer plus SCT. Okay, seems like it worked. And the signing as well. Nifty. Let's see what happens if we install this thing. So sudo ins mod sct dot ko. Huh, I got disconnected. Would you look at that? Exactly what I was aiming for, right? Or but it seems it killed the process rather. Is this really installed? It is. It is. Does it say anything in the messages? Oh, that's not good. What happened here? Bug kernel null pointer dereference. It's quite cool that it caught that actually. Without crashing everything. But I never dereferenced the null pointer, did I? I set it to 0. I use it for pointer arithmetics by adding this to it. And then I dereference. Maybe I shouldn't do it like this. Let's just set it to SCT, but let's cast this thing into static void double star. So let's remove this SCT. Module is in use. That's a weird one. Can we force this thing? Never mind. Let's just change the name of it when we compile it the next time. Okay, that was not popular. Maybe we can just put the static here. Okay, compile without warnings. So let's rename this to sct2.ko. And let's insmod it. Maybe we can't call this kill function when we're in kernel mode like this, because this initialization of the module is probably happening only in kernel land, and this kill thing is happening in user land. So I guess that might be why this is happening. At least it didn't crash this time. Maybe it's time we try this for real instead. Let's try to replace kill with a function that just returns an error each time. So let's call this well, this will be new kill. And it will be a regular function. So new kill, and it takes a PID t and an int. And then we do static. I'm not sure if this should be static, but let's try it. Static int new kill, we have PID t PID, and we have int signal. And actually we're not going to use any of those at this point. All we ever going to do is return with a -e perm, no matter what. That's our kill function. So what are we going to do? We're going to remove protection. We're going to change the syscall table by changing number 37 to the address of our new kill. And we're going to restore protection and return 0. And when we and maybe some message to successfully loaded. And when we unload, we're going to do the opposite thing. So we're going to remove protection again. We're going to set syscall table 37 equal to the original kill. We're going to restore protection. And let's add a PR info, set.o unloaded. Okay, something like this. Now we only need to define this protection thingy. So let's say static void remove protection void. And we're gonna have a restore protection as well. And this will be the asm instruction. Let's see. Let's move the string that they had. This right here. No, let's first move CR0 into EX. And let's move this number into seems to be too many digits. We have 2, 4, 6, 8, 9. Maybe it's right. This will move into EBX. Then we want to do not on EBX. So we remove that thing. And then we want to add from EBX to AX. That would be the right string, and finally we can move from EX to CR0. I think that is correct. And let's return. And the restoration of the protection should be pretty similar. The only thing we need to change is we need to remove this not thing. And let's see. Move this into EX. We move this string into EBX. Then we want to do OR instead. And this should be it, I think. Not entirely sure, but we'll see, won't we? And let's do let's change the name of this to SCT3. Let's save, and we need to go into the server and remove the old one. Let's do make clean first. And we'll remove sct.c. Let's change the make file so this will be sct3, and we'll make. Not a single error or warning. Let's see if we can load this thing. So sudo insmod sct3.ko. Okay. Sct. Okay, it's loaded. Has the message appeared yet? We need to do sudo dmask tail. Is this the old code or is this new code? Sudo journal this grep kernel tail. Let's see. Dmask. 7 minutes 54 was this, and this is 8:12. Seems to be rather new. Let's see what it says. Where do they start? Here somewhere. Insmod sct3. Warning. PID blah blah blah. Do one init call. CR0 is this. Let's see what it was the last time we crashed. Because then we didn't change anything. So it's this. And this. Okay, so at that point we did not change anything. Bug scheduling. It's not very easy to interpret these logs. We do get the registers here. FFFFFDA and EBX is the inverse of that. And this is still the same. But it is still running, isn't it? Our module. Maybe it does work. What if we were to try to kill something? Let's see. Sleep one. Is that still there? No. But PTS1 is. This should kill my other window. This one. Okay, it died. Unprotect memory. We take the contents of CR0 and we add it with the inverse of this. And what do I do? I move from CR0 to EX. I move from this. I move this value into EBX. So EBX should contain this value. Depending on, yeah, it should contain that value. Grep EBX TMP. And EBX is 3. Hexadecimal 3. So what is that? 1, 1. Let's see, what is this value? Deck. It is 65,536. So what's that in binary? Should be something like, let's see, 65,536. Should be a 1, 1, 2, 3, 4, 5, 6, and like 16 zeros, right? And AX at one point is this, and then 0. EBX is 3. All along, except for here. But why does it become 3? Maybe that's some other thing in the kernel somewhere. TA 44. How did he do it in his case? Write CR0 forced. As volatile he runs. Is that... Ah, wait a second. No? Yeah, we need to escape this thing. So all the percent should be double percent. Right, and let's use their thing as well. So percent %s, change asm to asm volatile. Is that it? Yeah. Whatever that means. When you use volatile variables, it usually means something like don't touch this with regards to the optimizer. But I'm not sure how that translates into the kernel, if it does at all. Are we able to remove this module, by the way? Doesn't seem like we are, or? No, not really. There's a lot of modules there now. So let's change this to SCT4. And same here. So we do make clean. We remove number 3. We make again. Bad register name. Oh, this should not be there. But it still gives us this output. I'm not entirely sure what this fourth order thing means. Let's see, GCC as some function. In this case, they do the double percent. So why can't I? I do only have one here though. But it seems to be complaining about all of them. Maybe it's because I don't have any arguments to it. So in that case, it should not be escaped. But let's assume that is the case, that we don't have any arguments. And this code compiles, but it crashes, right? Because this is the same thing that we did before, right? They do this asm linkage instead of static for the hooked function. So maybe that's it, that we are saving the function in some part of the memory which is not available or accessible. What about the saved one? Same there. Okay, so we do new kill should be asm linkage instead. Asm linkage. Okay. I wonder if the old one is interfering with this new one though. But let's try it once and see what happens. So let's tail the messages. And maybe let's just run it and see what happens. So is this SCT4? Yes. Sudo insmod sct4.ko. Boom. Alright, let's see. Insmod, and there's no log after that. That's good, right? Let's see if we can kill some stuff. So we are PTS4, so this is us. Can we even kill our own process? What if we do kill -9? It does work. It does not, however, when we kill, but we don't get an error message either, though. So I'm not sure if we are really affecting anything. This is still not returned. Alright, let's take a short break so I can reboot this machine, and then we'll continue. So, see you in a bit. Did you know that I made a book about computer networking? You will learn how the internet works and how everything works under the hood. It's a complete beginner's course, but it has some advanced elements as well. And you will learn network design and network security and all different kinds of stuff. For more info, check out books.drbirch.com. That is books.drbirch.com. Thank you for your support. Alright, you guys, welcome back. Let's see if we can't get this thing to work. I have rebooted my machine and I had a good night's sleep, so I come back with some new ideas. First of all, we need to update this address to the syscall table, because if we are using that Kassler technology, that basically means that this will be randomized each reboot. So let's see if that is so. Maybe we could write a simple bash script to recover the address for us. Yeah, why not? It's not a huge detour. So let's create something like syscalltable.sh. And we will take, no, we will not take any arguments. Let's see if I remember where those files were located. Well, we have the ksims, That we know, that is proc ksims, right? No, not ksims. What was it? Call sims with a K. So that's one. And then we have the sysmap, which had a very long path. Let's see, I did something like this. It was a part of the kernel debug package, if I remember correctly. Maybe it's called Linux debug. Yeah, this is the one. Alright, so let's list all those files. We did dpkg, that's tough to say several times in a row. And we give this package name, and we grep for, well, system something app. There we have you. Just see that it looks right. Yes, this is the one. So let's make two simple functions. Let's call the first one grab ksims. And it will have one argument, which is the symbol. And in case we don't have a symbol, then we will fail. I'll just do something like this. And exit one. But if we do have a symbol, what do we want to do? Well, first of all, we want to create a regular expression. So let's say regex is equal to, and we want to grab, let's see, we want to have a space or some kind of white space character. Then we want to have our symbol, and then we want the line to end. And then we simply grep extensively for this regex. And we want to grab the ksims file. Right, we are in the ksims file. I'm looking at the other one right now. So call sims, but it's the exact same format. That's good. And when we have grepped that, we want to take the first word. Like so. And by the way, maybe we should generalize this a little bit. Let's just call this function grab, and we'll have a symbol and a file. And we grep from the file instead. That way we can create our grab ksims function, and we can simply run grab with the argument and our ksims file. And then we can do the same for grab sysmap. So we grab argument sysmap. That's nifty enough, right? So let's see if it works. Let's do grab ks $1. And what did we call this? We called it let's find the directory first of all. I think it is in tmp and kernel, and we called it syscalltable.sh, and we give this. Let's change mod it. Grab ks command not found. We need to reorder, I guess. Bash is a little bit cranky when it comes to ordering of functions. Grab ks. Grab ks. This is the correct one. And if you wonder why I change mod each time, that's because I upload the file when I save, so it removes the executable flag. All right, seems like we get the right thing. Let's just double check. Call sims. Yes, that's right. And we should get the same thing, but another address if we do sm, because it should be offset a little bit. And that seems to be right. All right, so as before, this is smaller than this. That's good to know. And let's use this start CPU 0 thing. Maybe, by the way, we should add head -1, so we only get one line. And now we can create a function which grabs the actual. No, first we need to calculate the offset. And how do we do that? Let's add this as a constant. Let's just call it string for now. So ksims should be equal to grab ksims this. No? Let's do that again. K should be equal to grab ksims string. And sysmap should be equal to grab sysmap string. Sorry. And the offset will be equal to, by the way, let's call this dec, because this would be in decimal format. This will be equal to $K minus $S. And now we need to turn it into hex again. So let's do a printf. And we want to do %x. And we'll give our decimal. And we can do this actually, because this is what we aim to return. So then we have the offset. And then we can calculate our syscall table. By first calculating the offset. And our syscall table will be equal to, let's do this des thing again. So let's see, what will it be equal to? Well, first we need to get the address from our system.map. So grab sm target and we calculate this by taking the address plus the offset, and we return same as before. No, let's not do this. Our address as hex. And how do we do this? Well, we set the target equal to $1 if we have $1, that is. That is the first command line argument. But if we don't, we'll set target equal to syscall table, else we set it to what we have specified, 5. And the target address is equal to syscall table. Target. So we need to add an argument to this thing. if we do not have a TJT, and we want to error out. And let's change this to TJT instead. And then we'll simply echo this address and exit. All right. Let's see if this works. Let's try it on something else first. We want something which is inside of this case call sim so we can verify it. This one perhaps. Let's first see that we don't have multiple matches. No, that's good. So let's try our script, sct.sh, and we give this thing. Line 43. Oh, this should just be O. I was not hoping for that to happen. Zero. How can that be zero? Let's double check everything. If $1 is empty, target is this, otherwise target is what we specify. Target address is syscall table on that target, and syscall table sets this. O is offset. Address is grab SM target. Deck is address. Maybe we need to format it before we try to do any arithmetics. So let's do a formatted address is equal to 0x and the address. We give that instead. And we need to do the same here. So let's create a formatted k, which is equal to 0x k. A formatted s, which is equal to 0x s. And then we give this at both locations. Let's try this again. Value to great for base. This last one did not get formatted. 46. Right, we need an F. No. Yeah, we do. We need an FO also. Same thing, we do 0x O changes to FO. Okay, now I think it should work. Okay, we got something. If this is the correct one, we should get this x86 op int nope when we grab this from proc colsims. No, we should not have the 0x, by the way. There we have it. Okay, it works. Pretty nifty. And if we run this without any arguments, we get the address of our syscall table. Let's see if it has changed. It has not. Okay. Then we probably don't have any Castler. All right. It was a good enough exercise anyway. So, we crashed the kernel when we tried to do this kind of stuff. So the first thing I want to make sure is that we are doing the right thing here, that the calculations are accurate. So let's create an assembly file where we do the same thing. Let's call this tmp.asm. It will be pretty simple. We'll just do bits 32. We want to export the start label. And let's say the ECX register is our CR0 register, because we don't have access to CR0 as useland program. So ECX is our CR0. And let's put the value there that we got from the logs. So if we do this command and we grep for kernel, and let's grep CR0. So let's take this value and move it into the ECX. And we also need the value from here, this one. Let's copy it to be sure. So we move this thing into EBX. But before that, we copy into EX the ECX, like before. Then we do not on EBX to take the inverse. And we move into CR0. No, we do an AND operation. Between EX and EBX. And then we move into our CR0 or ECX from EX. Or maybe we don't need that last. Yeah, let's do it, by the way. And how can we see the output of this? Well, the easiest way is to do this little trick. We move into EBX and we move into EX01, and then we exit with that as an exit code. So this is basically the same thing as we do here. Move into this ordering is reversed, by the way, since this is the AT&T standard of writing assembly, but it's the same thing basically. So from CR0 to EX, then this value to EBX, we're not EBX, we AND those two together, and then we move it back. Let me just recreate my screen. And let's assemble this thing. So we do NASM, we want ELF. Maybe we should rename it, by the way. No, that's not. So we do NASM.elf and we take tmp.asm, and then we link tmp.o to tmp. Run this and we echo the return value 51. All right. How do we know if this is the right thing? Well, we need to look at this in binary. So let's see, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So this is our input. And this is our output. It does not seem right. Here we have 16 bits, so it's this bit we want to flip. And we do. And this is right. But at the same time, we get rid of this bit, which we should not. I think that has to do with the not. Probably it doesn't. It it doesn't inverse all the zeros. What if we specify that this should be down on a double word boundary? So we do anasm, we do ld, we run this again, same result. So maybe we should not use the not operator. There is something else available, which is more like a minus kind of thing. But I can't remember the instruction name. Let's see. x86 inverse instruction. Well, if we go to the not to begin with, is there a neg maybe? This operation is equivalent to subtracting the operand from 0. I think this is what we want. Let's try that. So if we do neg ebx, 1, 2, 3, 1, 2, 3, 1, 2, 3. Did we get a 0 this time? That's not right. Neg ebx. And ebx is this. What if we were to do it manually? What if we were to do sub ebx and we do ff, 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 ff. 1, 2, 3, 1, 2, 3, 1, 2, 3, no. Let's do anasm, let's do ld, and let's do this. And now we get a 1. What is the order of the sub? I think it's, are we taking this minus this or the other way around? Let's comment this out so we see what the result of our minus operation is. 1. How can that be? Sub EBX. So we take this. What if we were to move this into EDX instead? And into EBX we move this FF, 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 FF. And then we do sub EBX, EDX. Yeah. What do we get in this case? 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, now we get 2, 5, 5, so all ones. That's not right either. Can we do this another way? So basically we want to flip this bit and keep everything else intact. Can we just create a mask? Something like this. But with this one flipped. Let's see. So this to hex. Let's start over. No, not completely. I need to save that value. So let's move into, well, first let's move this value into AX, and into EBX we move this thing. I want to have it lowercase. And then we add EX and EBX. And we move it back into ECX. And just to print it, we move it into ECX. Okay, this time it must work. 1, 2, 3, 1, 2, 3, 1, 2, 3. Boom. 51. We get what we had from the beginning. 51. How is this possible? Because if we add something with all ones, it should not remove this or this or this. Ah, wait a second. Maybe the return values can only be 8-bit. That's right. So maybe we do get the right result and have all along. We're not able to print it. So all right, so we need to print it in 4 steps. We have this part already, but just to make sure, instead of just moving it to EBX, let's AND it into EBX with a mask of FF. This should probably render the same result. And let's do all this on one line. So we do this and ld tmp.o to tmp. And we run tmp and echo the result. Did I save this? 255. And EBX. Wait a second. No. Forgot one step. Move bytes into BL, CL. Okay, now we're back at the 51. So let's see if we can get this part. Well, we can just do this, right? So this time we should get a 0. Okay. And this time we should get 101. So what is that? 1, 2, 4, 5 we should get. And how do we grab that? We need to move the word bx from cx, and we need to end it with this. And we need to shift right EBX 8 bits. Still 0. Let's try the other way to do this, but we're still looking at this part. So let's see. We move into EBX this. And we do not EBX. We end it with EX, move it back to ECX, and then we take this third bit of it. Still 0. And what if we use this other instruction? What was it? We had not, and we had So let's see, x86 instruction complement. Neg. And what do we get now? Still 0. And what if we just move into ECX, EBX, so we can see what the negation of this is at the third position? Isn't it updating any longer? Oh. Let's do this. Well, what are we looking at? We're looking at this position. And if we negate that, it might not take these zeros into account. It's always difficult to handle those initial zeros when we're dealing with this kind of stuff. So when we run the not, we get all ones at this position. So this is all ones. Wait a second, we're moving a word. And we want this. So that's the problem. That's rather lame. So let's do the double word instead. Move the whole thing from ECX. We and it with this. Push it 16 positions. All right. 4. So we have 1, we have 2, and we have 4. 1, 2, 3, 4. Okay, well, that's the right one, isn't it? Because we're flipping this bit. Okay, that looks good. Let's try this as well to get the last one. 128. 128. So we have let's see. We have 1, 2, 1, 2, 4, 8, 16. 32, 64, 128. All right, so we got the right thing, and we got it all along. We just didn't know how to express it. Because this is what we had from the beginning, and this is what we have now, and as you can see, it's the exact same thing, except this bit is flipped. Okay, so our this version of the code works. So let's rewrite this in the other format. So we move into, let's see, this first line we don't want. But we want to move from CR0 to EX. Then we want to move the value FF, FE, FF, FF to EBX. Then we want to AND EBX with EX. And move from EX to CR0. Almost the same code as we had before, but not entirely. And we need to do asm volatile this. Need to do asm volatile and this, and let's copy this thing, paste it back in, same here, here, and here. So this is our code. Basically the same thing as before, only we skip this not step and we do it by masking instead. Move 00 EX, move blah 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 to EBX, and then we AND EBX EX, move EX to 00. And when we go back, yeah, we can probably use that same code. And let's cover our bases and change a couple of other things as well. Let's type def a function as a void function. Let's say the syscall table is not a static void. It's a static function pointer. So basically an array of pointers to a function, which is exactly what it is, right? So syscall table is equal to this. Let's do unsigned int instead. And let's not use this syntax because that might also be a problem. Instead, let's create let's do an int32, or let's just do unsigned int. Size. Let the size be equal to 37 times 4. So 4 is the size of a pointer, and 37 is position 37. So now we can set the original kill to be equal to the function of syscall table plus size. I think that is the right thing. But orig kill has a different signature, so let's do that signature instead. So no, let's try it this way first, at least. I'm not even sure if it compiles. So we take the original kill address from the syscall table. Maybe we need to do this though. And then we want to take syscall table plus size dereferenced and set that equal to the address of our new kill. And when we go back, we want to do the opposite thing. So we'll take syscall table plus size dereference to be equal to the function of the original kill. Okay, let's see what happens. So let's make clean, and let's make let's do an intermediate step. Void mem. Mem is equal to ct, and syscall table is equal to mem. Let's see if that works. need to do the same thing there. So this should be equal to let's do this, and then we set our kill to be equal to mem2. Okay, now it compiled. So let's see if it works. So we do sudo insmod, which is the latest. It's sct4 dot ko. Boom. Okay, it's in the list at least. And let's see what the logs say. Doesn't look too good. Doesn't seem to have added the key correctly. But I don't think that is the problem, right? Or are these logs only saying that that the kernel is tainted because of our signature? Maybe it still works. It is in the Alice mod list, after all. Let's try killing something. If we do kill this, it's still alive. But we didn't get an error either. And it still dies if we do this. Yeah. Hmm. It crashed when I tried to remove it. Well, we did get that message. But it complains about a page fault. I wonder if there's any way to clean the logs or insert some separation or something. It was so much easier before when it just logged to a regular ASCII text file. Why does everything need to change? And always for the worst. I wonder if we're even able to change this CR0 thing. What if we would just were to well, we can't really do this, can we? Mem is equal to this, and we need to do like that, or rekill equals to mem2. No. No, this is correct. Syscall table, because we are grabbing information at this point. And here we are changing it. So let's not change it. And let's not restore. Same here. Let's just do this. And let's double check our make file because the signature things worked before. We're assigning object.ko. It's weird that it doesn't work. lsmod grep sct, and it does not unload either. Well, let's try it again. Make clean, make. And we insmod sudo insmod. Maybe we need to change its name, by the way. sct4 to sct.ko. And we run sudo insmod sct.ko. Device or resource busy. Well, I suppose we need to reboot again. We'll be right back after this. All right, welcome back, you guys. Something interesting happened. I did a power off when I rebooted my machine. And now when I run my bash script, I get an entirely different address to the syscall table. At least I think it's different. Yeah, it's definitely different. Look at this. Okay, it hasn't changed much. It's still those 92 and almost a 270, but the 7 is an E instead. And then we have had a dB in front before, now we have 2 zeros. So it seems like this Kastler feature is working somehow anyway. Glad I created that script, because otherwise we had to recalculate this every time. Alright, so where were we? Right, I wanted to try to just run the remove protection code. And I remembered one other thing. What if the crashes and the stuff like that happens because we modify the EX and the EBX, and that is used somehow afterwards here? Even though we are calling a function, EBX might still be, well, it might still be used in that way. So let's preserve the registers. If we push EX, and let's do a push D, because it's a double word. And we do the same with EBX. And since we don't need to do any return values, we can just pop it right back. So we pop D, and this time we do EBX first. And then we pop the EX. EX. So by doing this, we save the current values of the registers, and we put it back when we're done. So I don't think that is the problem, but let's cover all our bases, right? Okay, so this time the only thing we're going to do, except for calculating some stuff, let's also, by the way, try to do, because I had one thought. Last time we ran this without commenting out stuff, it did not crash, but it crashed when we did this. So what if we were able to change function in the syscall table, but we changed the wrong one? Let's just do 37 here, since it is a void pointer, so it should be byte for byte. But this is a function pointer. I'm not sure how this works, actually. So let's try both ways then. But currently we're not using this, because the only thing we're going to do, except for saving the function address, is remove the protection. So I just want to see if that works or not. So let's save this thing, make sure it updates, and we make. Okay, so not push D. Maybe it defaults. I'm not very used to this syntax. Maybe it defaults to double word, so you don't specify that. And if you want a single word or a byte, you specify it. That would make sense, actually. So now the only thing is it warns us by this unused function, but that's not any problem. And we signed our se24.ko. let's see. Let's check the kernel messages first. Okay, so we are at this point. Let's see what happens. So we do sudo insmod and we insert sct4.ko. Killed. And if we check the messages now, it still crashes somehow. Let's dump this to the file and let's see what we got. Let's not do tail. Okay, so where were we before all this? We had just booted, so here somewhere. Okay, so this was the last thing. Loading out of tree module taints kernel. Out of tree. Module verification failed, signature and or required key missing. I wonder if all these errors and stuff happens only because the key is bad. But let's see, unable to handle page fault for this address, 92.93.04. 92.9, it's not this one. And the only thing we do now is, well, we do dereference this thing. But, and yeah, if we jump 37 bytes, we get unaligned. Maybe that's it. Page fault. Supervisor read access in kernel mode. Not present page. And CR0 has not changed, I think. Did it get loaded, by the way? Is it in our ls mod? It is. Can we unload it? Doesn't seem like. Well, let's try this again, but let's remove those two lines as well, because maybe the dereferencing is messing it up somehow. And let's save this under a new name. Let's go to SCT5. And perhaps we will be able to load this thing without having to redo the reboot. So we make clean, we make again. This time we do sudo insmod. Let's see which the last message is first. So dmask tail. let's save the timestamp. And now we do sudo insmod sct5.ko. Okay, it didn't crash this time. Is it in ls mod? It is. And there's a 0 here instead of a 1. So maybe we will be able to unload it after all. What if we were to do head-1 used by, yeah. So that's basically it. All right, so let's check the kernel logs again. And which was the last one? Yeah, we don't see any logs as of yet. Unable to access opcode bytes at blah blah blah. Wonder what address that is. Anyhow, this is for SCT4 still, but it's still interesting. But it seems like we were able to run this code, which is rather good. Let's also do this journal thing. -k. Okay, we get the same thing. Okay. So let's see if we can unload it. All right, everything seems to work. So that's good. Now we know there's nothing wrong with our assembly code, at least. That's one step closer. Another thing we could try is when we go to this point in the syscall table and recover this original function, maybe we should try to print part of this function, the opcodes, and see if we can make sense of them. Because if we go to this memory location and we get a couple of opcodes that seems to be, or at least possibly can be, the kill function, then we know we're at the right place. So how do we do this? Well, the easiest thing would be to grab our print hex function from birch utils. So let's go to code and birch utils. I think it will still work in kernel mode. Maybe not the entire library, but hopefully at least the print hex. Yeah, it's rather simple. Should work. So let's put this right here. And we need to change this to static void. And we need to define those data types. So type def unsigned char is int 8 and type def unsigned short int int 16. Let's do the other as well. Maybe we need them later on. So unsigned int is int 32, and unsigned long int is int 64. Okay, so we have a print hex function. If we return this to something that did not crash, and we go to this memory location, we find the syscall table, we go to the memory location of the kill function, hopefully, and we set the original kill to that. And if we now do print hex, and we want to do the int 8 version of the original kill. And let's do, I don't know, 64 bytes. And we can give a separator as well. Is it a char or a, yeah, it's a single char. So let's do X. And let's leave out the change of the syscall table for now. And we can't use the regular flush or print F, so we can use, what's it called, PR info. But that will create 1 log per character. Maybe we should alter this slightly. If we do int 8 buff, and we give it maybe quite big. And let's spin through this first. So we'll do 4 n is 0, as long as n is less than 60, less than size, n plus plus, and we want to set buff plus n equal to 0. Let's also create some temporary buffer of smaller size. Let's do 32. And let's do the same. So we do this and this. Less than 32, and we set tmp plus n is 0. So we zero out both of these. Then we can do sprintf into tmp this. Or maybe we don't have to go around the river for water. Let's remove the TMP and we go directly at our buff. And we put this, but first we put whatever we already have inside of buff. And we can do the same with this. So we do sprintf into buff. We give it buff and the delimiter. And when we are done with all of this, we do a PR info on buff. Maybe we should do this. All right, exciting. Let's see if we get anything. So let's make clean and we make it. What's this? M count undeclared. Maybe we need to include something for the sprintf. Let's try Linux sprintf.h. And what's this 93 thing? Let's do this. Void size. Just to silence the warning a little bit. Okay. See if we can find this thing. That's weird. I'm pretty sure there should be an sprintf. Let's see. On one of those pages that we were on, I remember seeing them using this. I think it's this one. Okay, so Linux kernel.h has sprintf. So why didn't we find it when we searched? Perhaps it is including in multiple levels and going outside of the Linux directory after a while. Well, let's try. So Linux kernel.h. And I closed the wrong one. And let's go into kernel and let's set this as our home. Make clean, jump down a little bit, clear the screen, run make, and boom. We still get this weird error. M count undefined. M count. Undefined. All right, let's try this fix. Defined but not used. So what if we just define it like this? M count undefined. environment variable contains PG flags. Maybe we should add kernel to the search. Some kind of mismatch between GCC and Clang. Have the .a to .o build fix. Config cc is Clang, but it's not Clang. We could try it, however. What if we set it to no? Let's try to set it to yes again after we've done make clean. Same thing. And what if we set it to no and we create something similar, but config cc is gcc? That is yes. Maybe it does not export these variables. I don't know how to do that. The make file. Can we do something like this? Maybe we can set it in the shell. If we export this to yes, and we export is clang to no, run make. Now we got another error. What if we do the other way around? Same thing. But what is causing this? Because we didn't have this problem before. Is it the include of kernel.h? Is it this print hex function or the call to sprintf? Let's see what happens if we just do this. We still get this error. And we didn't before. What if we go back here to kernel? We make clean, and we try to make this without setting our home to this directory. We still get this error. Why? We have basically the same thing as before. Well, we have the call to print hex. Let's try without. Still get the same thing. And if we comment out the entire function, but then same thing. What if we, well, we did add those type definitions, but can that really affect anything? Well, it's basically the only thing left. That's weird. It's the same code. This is really weird. What if we were to go to this directory and do make clean here? Maybe there's some leftover or something. No, I can't even do that. But how can the same code just stop working like that? Let's go through it line by line and see what changed. Okay, so now it's exactly the same as the thing that worked just a moment ago. Okay, now I really messed it up. Let's redo the kernel headers. If we remove this package, so apt-get purge this, and let's rename the directory to backup, and then we reinstall the Debian package manager segfaulted. I wonder if this SET module version 4 messed something up in the kernel. It's possible. Yeah, that's probably it. Let's remake this thing. We'll put everything back because I don't think there's anything wrong with our code. Like so. And we make clean inside of here. Okay, we can't even do that right now. I think it's time for a reboot. Alright, so let's look through our code a little bit while it reboots. If we get this print hex function to work as we intended to, then we will be able to print out the opcodes of the original kill function, if that is what we are pointing to. Hopefully it is. And then we need to translate those opcodes, basically running a disassembler, and we will be able to make sense if it's the right function, or at least if it's a function with processor instructions in it. Right, it responds. Let's set up the screen. Let's do this. All right, let's see if we can install this now. Okay, now it works. Good. So now we have this directory. Let's also grab our address 92.92.70. It's the same. Maybe it's because we just did a software reboot, I'm not sure. But let's see if we can compile. Oh, it worked. So we saved a lot of troubleshooting there, I think. It was an error which obviously had something to do with the code if we were to interpret it literally, but it was actually due to the kernel not functioning correctly because of our kernel module. So, all right. Let's see if this works now. If we first do a dmask and tail, the last one is this net thing again. So then we insmod our sct5.ko. It crashed this time too, because now we're not changing anything. The only thing we're doing is we're reading from this part of the memory. Oh well, we are writing to our own local buffer, but don't think that should be a problem, right? No, it can't be. I don't see that this could be a problem. But why does it crash? What does it say? Let's see. Where is the net thing? So this is the last one. Loading, blah, blah, blah. Unable to handle page fault at address 92.94.C0. Unable to access opcode bytes at blah, blah, blah. What can cause this? We are only trying to read. It's so difficult to debug kernel stuff. Let me see a little bit how they did it in their code. If we open up, let's see, references, and let's go to this one. And they had a section about system calls. Let's see. Okay, so this is the initialization function. Syscall cable symbol name, blah blah blah. Syscall table stolen. How do they define that? Unsigned long double star. Acquire syscall table. It's this one. So they basically just brute force looking for this case is closed thing. Well, they basically do the same thing that we do. The only thing that differs is they cast everything to unsigned longs. But that shouldn't really matter, right? So if we were to do this, but it need, wait a second, syscall table. And what does acquire syscall table return? Unsigned long double star. Well, since we already have the address, we should just do this. And the original kill should be the unsigned long int star of syscall table 37. And let's define the syscall table. Let's remove this function thing. And we'll define this as unsigned long int double star. Let's see if this compiles. It does. I wonder if we can install it. We still have this old thing running. Let's see what happens. That can't be good. You know what? Let's reboot one last time. If this doesn't work now, we will be done for the day. Because now we are basically doing exactly as they are. And we're not even touching anything, changing anything. By the way, this is commented out, but maybe we should alter this anyway, so we don't forget about it the next time. So basically, syscall table 37 should be equal to the unsigned long int star of this. Let's just see one thing. Yeah, they don't do the ampersand. They cast this to a void star. So this is cast to a void star, and when we change, we cast it to an unsigned long, and this. Alright, now we do the same. So let's log into this thing, and I will not start screen or anything, I just want to see if this works. So let's go into kernel, no, tmp, then kernel, and we run make. We do sudo insmod sct5.ko, and it's killed. Oh, we did not change the address. Has it changed? No, it doesn't seem like. It's the same error again. Page fault. Maybe this has something to do with me running this on a 32-bit machine. Maybe it works a little bit differently, because we only have, well, we can't cover the entire memory addressable. So perhaps we need to change the page somehow when we're in kernel mode. I need to read up on that a little bit. But anyhow, that's enough for today. I hope you have liked this episode and will continue watching this series. Please like and subscribe so more people can watch this content. And thanks for watching. Thanks for today.